Chapter 7, Part 4, Mechanical Energy. In this part, we will talk about the second form of mechanical energy, which is called kinetic energy. The kinetic energy of a moving object is equal to the work required to bring it to its speed from rest. If an object is moving, then it is capable of doing work. And this means the object which is moving has energy due to its motion. This energy is called kinetic energy. Kinetic energy depends on the mass of the object as well as its speed. In mathematical terms, kinetic energy is equal to half the mass multiplied by speed square. And be careful here, the speed in the equation is squared. Now, when you throw a ball, you are doing work on it. And then it will leave your hand with a speed. The moving ball then can hit something and push it, so it is capable of doing work. The amount of kinetic energy the ball has is equal to the amount of work you did on the ball. Again, note that the speed in the equation of kinetic energy is squared. So this means it takes 4 times the work to double the speed. Because when you double the speed, the kinetic energy will be 4 times. Which means you need to do 4 times of work to give the object that amount of energy. An object moving twice as fast will take 4 times as much work to stop. Now, work and energy are related, not only because they have the same units, but also by a famous theorem that connects work and energy. According to the theorem, whenever work is done, energy changes. Now, to increase the kinetic energy of an object, work must be done on the object. If an object is moving and you want to stop it, you have to apply work on the object to bring it to rest. The change in kinetic energy is equal to the total work done, to the net work done. This is the famous work-energy theorem. So the work-energy theorem describes the relationship between work and energy. The total energy the total work done on the object will give rise to change in kinetic energy. Now, if you are pushing an object, for example, and the object doesn't move, so you are not doing work. And so the kinetic energy of the object doesn't change. So no work, no change in kinetic energy. If the floor is slippery, then by pushing the object, it will move and it will acquire speed. The amount of work you are doing on pushing the object will equal to the change in kinetic energy of the box. The work-energy theorem applies also to decreasing speed as well. So, the more kinetic energy an object has, the more work is needed to stop it. Twice as much kinetic energy means twice as much work needed to stop the object. Due to friction, energy is transferred both into the floor and into the tire when the bicycle in the picture skids to a stop. Now, an infrared camera reveals the heated tire track on the floor, as you can see in picture A. It also reveals the warmth of the tire, as clear in picture B. When a car brakes, the work is the friction force, or is supplied by the friction force due to the brakes. And this work is calculated by multiplying the friction force times the distance over which the friction force acts. A car moving at twice the speed of another car will have 4 times as much kinetic energy. Therefore, it will require 4 times as much work to stop. Since the frictional force is nearly the same for both cars, so the faster car will take 4 times as much distance to stop comparing to the slower car. Let's think about this problem. A friend says that if you do 100 joule of work on a moving cart, then the cart will gain 100 joules of kinetic energy. However, another friend says this is not totally true. It depends on whether or not there is friction. What is your opinion on these statements? Well, although you do 100 joule of work on the cart, this may not mean the cart will gain 100 joules of kinetic energy. And the reason is because friction will take part or some of that energy and transfer it into heat. So how much kinetic energy the cart gains depends on the net work done on it, not just on the work you did on the cart. Another thing, another question to think about: when the brakes of a car are locked, the car skids to a stop. Now, how much farther will the car skid if it's moving 3 times as fast? Well, if the car is moving 3 times as fast, it means it will have 9 times as much kinetic energy. Therefore, it will require 9 times as much work to stop it. And this transfer into 9 times the distance.